Asteroids are rocky bodies that orbit the sun. They are much smaller than planets. Think of them as cosmic leftovers from the early solar system. There are millions of asteroids, and most of them live in a region called the asteroid belt. The asteroid belt sits between the orbits of Mars and Jupiter. These space rocks come in all shapes and sizes. Some are as small as a car, while others are hundreds of miles wide. The asteroid belt is like a giant cosmic junkyard. It's full of debris left over from the formation of the solar system. Imagine a chaotic cloud of gas and dust swirling around the young sun. Over time, this material began to clump together. Gravity pulled in more and more dust and gas, eventually forming the planets. But not all of the material became planets. Some of it remained as asteroids. The formation of asteroids is a fascinating process. It all started billions of years ago when our solar system was just a swirling cloud of gas and dust. This cloud, called the solar nebula, began to collapse under its own gravity. As the cloud collapsed, it spun faster and faster, flattening into a disk. At the center of this disk, the sun ignited, blasting out heat and light. The remaining dust and gas in the disk continued to swirl around the newborn sun. Asteroids are like time capsules. They hold clues about the early solar system. By studying their composition, we can learn about the conditions that existed billions of years ago. Most asteroids are made of rock, but some contain metals like iron and nickel. Others are rich in carbon, a key ingredient for life. The composition of an asteroid depends on where it formed in the early solar system. Types of asteroids, a diverse bunch. In the vast expanse of space, asteroids come in a fascinating array of shapes, sizes, and compositions. These celestial bodies, remnants from the early solar system, offer a glimpse into the building blocks of planets and the history of our cosmic neighborhood. Not all asteroids are created equal. Each one tells a unique story about the conditions and processes that shaped it. From tiny pebbles to massive boulders, asteroids vary greatly in their physical characteristics and chemical compositions. There are different types, each with its own unique characteristics. These differences are not just superficial. They reflect the diverse environments in which these asteroids formed and evolved over billions of years. Some asteroids are dark and dusty, while others are bright and shiny. The dark ones are often rich in carbon, giving them a sooty appearance, while the shiny ones may contain metals that reflect sunlight. Some are made mostly of rock, while others are rich in metals. The rocky asteroids, often composed of silicate minerals, can be quite varied in their appearance and structure. Metallic asteroids, on the other hand, are typically denser and can contain valuable metals like iron and nickel. The three main types of asteroids are C-type, S-type, and M-type. Each type has distinct characteristics that set them apart from one another, making the study of asteroids a complex and intriguing field. C-type asteroids are the most common. These carbonaceous asteroids make up about 75% of known asteroids and are found primarily in the outer regions of the asteroid belt. They are dark and carbonaceous, meaning they contain a lot of carbon. This high carbon content gives them a dark appearance, and they are thought to be some of the most ancient objects in the solar system, preserving the primordial material from which the planets formed. S-type asteroids are made mostly of silicate rocks and are brighter than C-type asteroids. These stony asteroids are found mostly in the inner asteroid belt and are composed of silicate minerals and nickel iron. M-type asteroids are metallic, containing a lot of iron and nickel. These metallic asteroids are less common but are of great interest due to their potential for mining valuable metals. They are thought to be remnants of the cores of differentiated protoplanets that were shattered by collisions. Close encounters asteroids near Earth. While most asteroids reside in the asteroid belt, some venture closer to Earth. These are known as near-Earth objects, or NEOs. NEOs are asteroids and comets whose orbits bring them within 120 million miles of the Sun. While this may seem like a vast distance, it's relatively close in astronomical terms. Scientists keep a close eye on NEOs, as even a small asteroid impact could have devastating consequences for our planet. The threat from above asteroid impacts. Asteroid impacts are a real threat to life on Earth. While large impacts are rare, they can cause widespread destruction. A large asteroid impact could trigger earthquakes, tsunamis, and wildfires. The dust and debris thrown into the atmosphere could block out the sun, leading to a global cooling effect known as an impact winter. This impact winter could disrupt agriculture and lead to widespread famine. The dinosaurs know real-world examples of impacts. Throughout Earth's history, our planet has been shaped and reshaped by the forces of nature, including the dramatic impacts of asteroids. The Earth bears the scars of past asteroid impacts. These scars, often in the form of craters, tell a story of cosmic collisions that have had profound effects on our planet's history and evolution. One of the most famous examples is the Chicxulub crater in Mexico. This colossal crater, hidden beneath the Yucatan Peninsula, is a silent witness to one of the most catastrophic events in Earth's history. This massive crater, over 110 miles in diameter, is thought to be the result of the asteroid impact that wiped out the dinosaurs 66 million years ago. The sheer size of the crater gives us a glimpse into the magnitude of the impact. The impact triggered massive earthquakes, tsunamis, and wildfires. These immediate effects would have been devastating, causing widespread destruction and chaos across the globe. The dust and debris ejected into the atmosphere caused a global impact winter, plunging the planet into darkness. This prolonged period of darkness and cold would have drastically altered the climate, leading to the extinction of many species, including the dinosaurs. Scientists believe that the asteroid impact released energy equivalent to billions of atomic bombs, creating shockwaves that traveled around the world. The force of the impact was so immense that it vaporized rock and sent molten material flying into space. Evidence of this catastrophic event is found not only in the Chicxulub crater but also in the fossil record. Paleontologists have discovered a layer of sediment, rich in iridium, a rare element often associated with asteroids, that marks the boundary between the Cretaceous and Paleogene periods. Understanding these past events helps us prepare for future asteroid impacts. While the likelihood of a similar event happening in our lifetime is low, the potential consequences are so severe that scientists continue to study and monitor near-Earth objects. Through advancements in technology and international cooperation, we are better equipped to detect and potentially deflect hazardous asteroids, ensuring the safety of our planet for future generations. Planetary defense tracking and monitoring asteroids. The good news is that we are not sitting ducks. Scientists and engineers around the world are working on ways to track and deflect potentially hazardous asteroids. The first step is to find and track these space rocks. Astronomers use powerful telescopes to scan the skies, searching for any objects that might pose a threat to Earth. Once an asteroid is discovered, its orbit is carefully calculated to determine if it might collide with our planet. Saving the world. How to stop an asteroid. Imagine looking up at the night sky and knowing that a massive asteroid is hurtling towards Earth. The thought alone is enough to send chills down anyone's spine. But fear not, humanity has been preparing for such a scenario. If we do find an asteroid on a collision course with Earth, we need a plan to deflect it. Scientists and engineers around the world have been working tirelessly to develop strategies that could save our planet from such a catastrophic event. Several methods have been proposed, each with its own unique approach and technology. These methods are designed to either change the asteroid's path or break it into smaller, less dangerous pieces. Kinetic impactor. This involves slamming a spacecraft into the asteroid at high speed, altering its trajectory. The force of the impact would be enough to nudge the asteroid off its collision course with Earth. This method requires precise calculations and timing to ensure the spacecraft hits the asteroid at the right angle and speed. Gravity tractor. This involves using a spacecraft's gravity to slowly tug the asteroid off course. By positioning a spacecraft near the asteroid, the gravitational pull between the two objects can gradually change the asteroid's path. This method is more subtle and requires a longer time frame to be effective, but it has the advantage of being a controlled and predictable process. Nuclear option. This last resort option involves detonating a nuclear weapon near the asteroid, vaporizing part of its surface and creating a jet of material that would push it off course. While this method is the most dramatic and potentially dangerous, it could be the only viable option for large or fast-approaching asteroids. The explosion would need to be carefully calculated to avoid breaking the asteroid into multiple hazardous fragments. Each method has its pros and cons, and the best approach will depend on the size, composition, and trajectory of the asteroid. Scientists must consider factors such as the asteroid's speed, distance from Earth, and the time available before impact. Ongoing research and simulations help refine these strategies, ensuring that we are as prepared as possible for any potential threat from space. The collaboration between international space agencies, researchers, and engineers is crucial in developing and implementing these life-saving techniques. With continued advancements in technology and a proactive approach, we can protect our planet from the dangers lurking in the cosmos. Conclusion. Living in a cosmic shooting gallery. We live in a cosmic shooting gallery. Asteroids are a constant reminder that space is full of potential hazards, but we are not helpless. By studying asteroids, tracking their movements, and developing deflection strategies, we can protect our planet from these celestial threats. The future of humanity may depend on our ability to master the cosmic shooting gallery and defend our planet from the dangers that lurk in the vastness of space.